Imagine you are driving a car. You are going at 70 miles per hour on the freeway. You turn your head to see the squirrel to your left when suddenly a wall appears out of nowhere. Ouch! You've just had an accident and a collision. You decelerated from 70 miles per hour to zero in a matter of a few seconds. If you plot out the graph f of t during a regular deceleration not in an accident, and also the graph f of t during the collision, we notice a significant drop in deceleration time with the accident. With this in mind, we will be able to find the impulse of your car crash. Most of you must be wondering what impulse is. Impulse is the change in momentum of your car as well as force multiplied by the change in time. This leads to the conclusion that if an object decelerates from the same starting speed to rest, it will have the same impulse irrespective of how much time was taken to decelerate. In an accident, the time taken to reduce the car's speed from 70 miles per hour to rest is very short, which leads to a higher peak in the f of t function than during a controlled deceleration. However, the idea of impulse can be used to reduce the force upon impact. The idea is to increase the amount of time that the force during the collision is acting upon the car. Now, let's find the impulse of your car crash. In order to find this, we can calculate the exact amount of area under the curve by using an integral of your force function with respect to time. An integral will allow us to find the area from the curve of the function to the x-axis. In order to understand what an integral is, we will start off with Riemann sums. Say you are given a function and you want to find the area under the curve. You decide that you are going to make approximations using rectangles. You first draw two rectangles and find that it is not quite right. You then decide to draw four rectangles to get a better approximation. You soon realize that the best approximation would mean that you'd have to draw an infinite number of rectangles under the curve to get an exact value. Integrals are essentially the area of an infinite amount of rectangles under the curve whose length is the y value and whose width is dt. Thus, we can find the exact value of the area under the curve with no over or under estimates. Now that you know about how to find the impulse given the graph of f of t, let's learn more about some safety precautions that must be taken to reduce the force felt by the passenger during an accident. But before we dive into that, let's learn about something called the head injury criterion. This criterion gives a number which describes the impact on the head of the driver during an accident and is used by the U.S. National Highway Traffic Safety Administration to give star ratings for each vehicle based on overall safety for consumers. This number is the maximum value over the critical time period T1 to T2 inside the square brackets. If you notice, the quantity described inside the brackets uses the average value of the acceleration function during the interval t1 to t2. An average value of any function over a certain interval is the area between the function and the x-axis divided by the change in the x-axis. In this case, we have an acceleration function of the car during the accident, and the average value gives us the average acceleration during a certain interval. This value is then raised to the power of 2.5, which is the index chosen for the head based on experiments. This number is then multiplied by the change in the x-axis to get a value on the h of t curve. The HIC is the maximum value out of the family of all the h of t functions, which can be derived from the varying delta t's and the original acceleration function. Finding the maximum value of each h of t curve would require optimization of the equation inside the bracket and then optimization of the function that gives the maximum value of the family of the h of t functions. Optimization is when you find the maximum or minimum value of a given function using its derivative to find a slope of 0 where there is a sign change. We will explore the concept of optimization in a later video as it requires more advanced skills to optimize this function. Now that you understand what the HIC is, let us understand how this number is used to determine the safety of a car. HIC are values given after a crash test by the experimenter. The higher the value of the HIC of a car, the more chance there is for the head of the passenger to get injured. A value of 1000 is considered life-threatening, and so under the provisions of the US Advanced Airbag Regulation, a maximum value of 700 is allowed for a car to be released in the market. This number can greatly be reduced using seatbelts and airbags, as they increase the time of impact, which in turn reduces the peak achieved in a force versus time graph. The closer that an HFT function gets to a low and flat curve, the safer it is for a passenger to be in the car. Remember, safety belts save lives and airbag saves heads.